Welcome to our presentation on Pilot Edge, Distributed Resource Management along the Edge to Cloud Continuum. My name is Andre Lukau, and this is joint work together with Kartik Rathan and Shantanu Jha from Rutgers University and Brookhaven National Lab. The Internet of Things is becoming an essential part of many scientific and industrial applications. Light sources like the National Synchrotron Light Source 2 at the Brookhaven National Lab are generating data at growing rates of up to 20 gigabytes per second. In farming, sensors and data is used to help essential aspects like energy and water usage, as well as yields. IoT is also increasingly being used in manufacturing environments. Data collected in such environments can be used for use cases such as predictive maintenance of machines or quality inspections. However, in order to really benefit from the edge, typically nowadays applications need to utilize multiple layers of infrastructure from the edge to the cloud, the so-called edge to cloud continuum. Doing so is not quite as straightforward as it sounds, because first of all, you have to overcome a large heterogeneity. The further you get to the edge, the more diverse your environments, more diverse your sensors, your compute environment is going to get. At the same time, on the cloud side, you have to combine different programming models and paradigms, for example, MPI for simulation, Spark for data processing, and maybe some more advanced deep learning frameworks. Overall, this environment is highly distributed, but also highly dynamic. Meaning, for example, the network can go up and go down. So you really have to constantly tune your application to the current state of your resources and your environment. As you can imagine, the provisioning of resources and the execution and management of tasks in this environment is very challenging. Just simple questions, for example, what should be the right amount of resources that should be assigned to a certain layer in your topology is a very complicated one and typically requires the exploration of various trade-offs. Second, finding then the optimal execution strategy for a given resource topology for an application is another important challenge that software developers in the edge to cloud continuum face. In this paper, we propose Pilot Edge. Pilot Edge is an abstraction that simplifies the interface to using distributed resources along the edge to cloud continuum. It aims to hide a lot of the complexity of dealing with resources and lets the application really focus on application logic and the ability to respond to certain types of events. Pilot Edge, as the name suggests, is based on the Pilot abstraction, an abstraction that was invented in the context of high-performance computing in order to support task parallelism on high-end parallel machines. But what is a pilot job? A pilot job generalizes the concept of a placeholder or container job to provide multi-level scheduling and allow the application to control its resources and manage resources more with respect to their application objectives. So how does it work? Here in this figure, you see in the user space, you have the user application. The pilot job system we implemented is residing in user space, giving the user a lot of control on how to handle and instantiate it. The user application comprises of multiple tasks. However, it will not directly execute those tasks on the resources that you see in the bottom of this graph. It will basically use these so-called pilot jobs. Pilot jobs are container jobs. They're being queued at the resource manager. The resource manager then starts the containers, and the containers are then managed by the pilot job system. And the pilot job system can then be used by the application to directly submit their tasks to these containers. So much about pilot jobs. As I said before, pilot job systems have been invented, explored in the context of high performance computing. Over the last couple of years, we have been seeing an increase in the requirements with respect to managing data associated with compute, because also in particular in IoT environments, we typically have to manage complex data flows, data pipelines across the edge to cloud continuum. So in the past, we have been extending the pilot job system to pilot data and pilot Hadoop to facilitate the needs of supporting advanced data parallel data processing on top of data. Pilot streaming extends this capability again to support unbounded data feeds. And Pilot Edge now adds a second new component in there, which is basically the edge compute unit that allows us to really orchestrate highly distributed resource types within a single application. Let's have a look at the application the Pilot Edge abstraction was designed for. In order to do so, it helps to look at common deployment modalities for edge to cloud applications. In the past, we have seen a lot of edge-centric applications, meaning these are applications that do everything in a closed, siloed edge environment, from the sensing, data pre-processing, analytics, machine learning inference, and machine learning training tasks. Everything was basically done on the edge. This has a big disadvantage, right? Because you cannot easily or simply infuse external knowledge, external intelligence into this environment. You're always somehow constrained to this kind of siloed environment. The other extreme are cloud-centric applications that only do the minimal of their work on the edge, but basically rely on the cloud for everything that's a bit more advanced or intelligence. Typically, these types of applications are limited by the amount of data you can move from the edge to the cloud. In addition to that, typically maybe have some data privacy and data security constraints that prevent you from moving the data to the cloud. So what we see now is the newest trend is we have so-called hybrid applications that really want to utilize every layer of the infrastructure and optimal place every task very close to the data and on the right layer to respond to that. However, progress has been hampered by the need to overcome a diverse set of resources, and also by the need to carefully orchestrate the task, because obviously the sensing task needs to fit to the pre-processing task, and the pre-processing task needs to fit to the analytics task. So it's very complicated and very work intensive, and really to set up a vibrant hybrid edge to cloud applications. So what we are proposing now is the Pilot Edge abstraction that really simplifies application development for those kind of environments by decoupling low-level resource management and really high-level application logic. So how does Pilot Edge work? On the bottom two layers, you see the pilot framework and the resources. This is basically what we saw in the high-level schematic a couple of slides ago. And this is the pilot job system. And this is the implementation here. You see we use flexible plugin architectures on all levels that enables the framework really to flexibly orchestrate tasks, data, compute environments like, for example, Dask and Spark, but also programming systems like Kafka. It's on to the application or maybe to a system administrator to configure the pilot's initial to an application deployment. And the application itself and basically can orchestrate the application workload using the Pilot Edge abstraction, which is a serverless abstraction that provides a function as a service interface. Basically, the application has to define their processing functions on the edge and the cloud. The system then will handle the transparent orchestration of those functions, but also of the data flows for those functions. Further, Pilot Edge provides some coordination and parameter services, for example, for sharing model weights across the edge to cloud continuum. Let's have a look at the abstraction. This is the simple API. As said before, simple functions, process edge, process cloud, and produce edge. They all take a context object, provide the context for providing contextual information, and the data is provided as an input parameter. And there's also an API for sending of data to the next level of the topology. So this is basically what the application developer can focus on. And then it's up to the instantiation of the application, meaning assigning those tasks to resources. As I said before, the pilot job systems basically are allocating the resources, and they are passed basically to this edge to cloud pipeline object, in addition to the context and the function pointers. In order to evaluate the system, we implemented a distributed edge to cloud pipeline, one in the data center in the EU only on the Leibniz Supercomputing Center. And in the second scenario, we have the data production in the US, and we have the programming and the data processing system in the EU. We mimic edge tasks using a very small VM, and for every task, we assign roughly 1 core and 2 GB of memory. Unfortunately, the VMs are not entirely comparable between the US and the EU cloud there, and we use a more powerful VM for the processing and the programming nodes. We use the Mini-App framework, and I encourage you to read the reference below here for synthetic data generation. It really provides you the ability to synthetically explore your different application workloads in the Edge to Cloud Continuum without really the necessity to implement a real-world application. And particularly in that case, we explore different machine learning models for outlier detection, specifically k-means, isolation force, and auto-encoders. We made some interesting observations. For example, obviously the network latency has primarily an impact when we look at the baseline, the blue line performance, which is basically sending the data across the pipeline without any processing. And on the throughput, we see a bit more diverse picture. We see that the intercontinental bandwidth particularly limits the throughput for the baseline k-means, not so much for isolation force, but definitely not for auto-encoders, which are definitely in that case compute limited by the processing nodes. You use such a 10-core machine with 44 GB of memory. The auto-encoder model is both very memory intensive, but also very compute intensive, and would, for example, benefit from GPU processing capabilities. This is, for example, one parameter one could investigate in a future experiment. Let's summarize our experiment. And we utilize the pilot edge, abstraction, and implementation for implementing a machine learning outlier detection pipeline as found in many edge to cloud applications. We investigated the impact on latencies, bandwidths, and model complexity, and demonstrated how easy it is for the application developer to really assess the trade-offs between those parameters. Let's come to the conclusion of our work. Pilot Edge addresses important challenges of computing along the edge to cloud computing, heterogeneity, dynamic and distributed environments, and last but not least, the ability to efficiently manage resources and tasks. In the future, we're going to extend Pilot Edge, for example, to support more complex infrastructure topologies. We're also going to investigate advanced resource management and scheduling strategies, for example, energy-aware scheduling, and new types of workloads like federated learning. This brings our presentation to the end. Thank you very much for your attention. Please have a look at our paper. Thank you and goodbye.